In this video, we will do a quick overview of GUI and Exiv, then a technical deep dive of its architecture followed by a quick walkthrough of the code. GUI is in a separate repo that you have to run after you have started the Exiv server. Let's look at how it functions. Start up the GUI and navigate to Qwen3 TTS app. Select a custom voice, enter the text, and click Generate. The generated voices show up on the right side.
Hey, what's up?
Hey, what's up?
You can also upload your own voices, but if you don't provide the reference text, they will run in X vector mode.
When I was a kid, I feel like you heard the term.
Let's generate from the uploaded voice.
Hey, what's up? When I was a kid. Hey, what's up?
In X vector mode, the output voice can be unpredictable depending on the text. Let's try the exact same text.
When I was a kid, you heard the term.
The output voice now sounds much closer to the original. Before going into the architecture overview, here are some core features. Qwen supports voice cloning from 3 seconds audio. It has two modes for this, X vector and ICL. X vector is purely based on the reference audio, while ICL requires both the reference audio as well as the reference text. There are 3 variants of the model. Base variant supports voice cloning. Custom voice variant has inbuilt custom voices, and the voice design variant supports creating new voices through text descriptions. One standout feature of this model is its super low word error rate, which we will see in the next slide. Also, at the time of release, this model was SOTA, trained on roughly 5 million hours of data. This model is also relatively lightweight at around 1.7 billion parameters. If you work with video models, you would know that they can easily go till 20 billion parameters, and even the smaller ones can go above 5 billion parameters. With 1.7 billion parameters, this can run comfortably on most consumer GPUs. This supports low latency audio streaming and also has native multilingual support for 10 languages, and you can easily use it to generate cross-lingual data, like using the same voice to generate English and French audios. Now let's look at WER benchmark. You can see that at the time of release it was beating both Minimax and 11 Labs, and by a lot. If you look at Chinese, the difference in scores is night and day. Same with English. Weirdly enough, it's their smallest model that is beating 11 Labs. It outperforms them in other languages as well, like Italian, Korean, French, and Russian. Now let's jump into the architecture deep dive. Their technical paper provides a nice visualization of the architecture. The main inputs of the model are the text tokens, think tokens, and the speaker embedding. Looking at this diagram, you would think that this is some kind of dual channel setup, but in reality, we are simply summing these two up. That's why we have these pad tokens, which are basically zeros for that particular token category. This is how the model functions. The main talker module generates the first semantic token. The MTP module, which I call subtalker, generates the rest of the acoustic tokens from 1 to 15. These 16 tokens are then used as prefill for the next token generation. Another thing is that the speaker embedding you see here is shown as one input, but in reality there are multiple modes of input. As we have discussed before, we have two modes, X vector and ICL. If we use the X vector mode, we only require the speaker embedding, but if we use the ICL mode, we will need both the RVQ codes and the reference audio transcript. Let's see how the speaker embeddings are generated. This entire architecture is directly taken from the Akapa TDNN paper of 2020. First, we extract the MEL spectrogram from the audio. As we go along the layers, you will notice that we ultimately get rid of the temporal dimension, which is the core function of this architecture, to generate speaker embeddings of a specific length. TDNN uses progressively higher dilation values as it goes through the layers. Having higher dilation with the same kernel size makes the model pay attention to frames that are not immediately adjacent. The core intuition here is to enable the model to see more context without more parameters. With different dilations, the model is able to understand different relations between the time frames. The squeeze excitation can basically be viewed as channel-wise attention maths. Starting with the channels, we first calculate their averages. This is the squeeze part. MLP's function is to calculate the attention weights for the specific channels and kinda also learn their order of importance. These calculated attention scores are then used to calculate the final, scaled average values. From squeeze excitation, we get the weighted output based on channel importance. These feed into the ResNet. The ResNet splits the channels into groups and processes them with a cascade pattern. G0 sees the raw frequencies. G1 sees the local window with only one convolution. G2 sees a larger context with two convolutions in addition to what G1 saw. This is more expensive than the standard ResNet, but captures much more richer representations with the same parameter count. Attentive statistical pooling. Unlike the standard pooling, this does the attention calculation through learned weights. This is done through an internal TDNN network. The calculated attention is then used to calculate the weighted mean and standard deviation. This is the critical step because it's here where the temporal dimension is squashed and averaged out. One thing to note is that the earlier TDNN network was more focused on hierarchical feature extraction from the audio, identifying frequency patterns, phonetic structures, and multi-scale temporal features. The TDNN inside ASP, however, serves a different purpose. It computes attention weights to identify which time frames contain the most speaker discriminative information, enabling the weighted averaging that produces the final statistics. The MIMI encoder takes raw audio and squeezes it down into a compact digital format through three main steps. First, a specialized CNN called CNN, Squeeze Excitation Audio Network, dramatically shrinks the audio by 320 times. Unlike a typical image neural net that looks at 2D pictures, CNET uses 1D convolutions that slide across the audio waveform over time. It's built specifically for sound. It uses strided convolutions to quickly downsample while preserving important frequencies and dilated convolutions that act like a zoom lens, letting the network hear context from far away, like entire syllables, without needing tons of layers. It also has squeeze excitation blocks that act like a volume knob, automatically boosting important frequency channels, like vowel sounds, and turning down less useful ones. Next, an 8-layer transformer looks at this compressed signal to understand longer range relationships, like how sounds blend together across words or phrases. The final layer generates the RVQ codes. One thing to note is that due to the nature of a kappa TDNN, it squashes the temporal dimension and any other property that depends on it, like emotional tone or prosody. Since speaker embedding also holds a lot of vocal characteristics of the speaker, you can't simply add a second reference through the RVQ or ICL channel to mix voice characteristics. You can check the complete code at my GitHub. Here is the short snippet explaining the core working. First, the text is converted into the chat.ml format and then tokenized. The reference audio and text is then used to create the ICL parameters as required by the model. Input IDs, ref IDs, and ICL parameters are passed into the generate method along with the generation config. Enable chunking parameter can be used to set automatic chunking, as this model particularly struggles with longer generations. As Exiv is built for modularity and allows easy addition of new features through hooks, the chunking is enabled through the audio context hook that you can check in the code. The output is finally decoded in the wave format.